Hi, I'm going to cover Kirkwood, and I'm going to speak in this tone. So if you don't hear me, or if you hear me speak less loudly, please tell me, and I will try to keep it in this tone. So I'm going to cover Kirkwood. Regarding Kirkwood, I do have slides. I'll post them. This is not working, so I'll post them, and I'll write like whatever is on the slides right now for you guys on the board. So what does Kirkwood talk about? Kirkwood is mostly focused on how do we store memory, how does memory work. And after considering a couple of options, like, okay, maybe we store memory in the way that the neurons are connected, or maybe it's in the morphology. After considering those and looking at their limitations, that not that much could actually be stored in those things, he concludes that maybe it is on the synapses, because each neuron has many synapses, and if each synapse is independent of any other synapse on the same neuron, then you can have so many states, so it can store a lot of memory. So it's good for memory. And then he starts talking about concepts like LTP and LTD. So what is LTP? It stands for long-term potentiation in a synapse. And it can be drawn. This is EPSP, which is excitatory postsynaptic potential. And if you look at it, like if it's pretty low at 0 here, and you have a stimulus to induce the LTP is going to look something like, well, first you're going to depolarize, but you're going to stand in that depolarization stage for a long period of time. Hence the long-term potentiation term. So a bunch of things to note about it is that it's lasting, so you can have a memory for a long period of time. It's non-decremental. And he talks about Heptrel, and this could be very similar to Heptrel. Heptrel says that cells that fire together should wire together. So if A potentiates B, then A should become over time more efficient in potentiating B, and LTP could have something to do with that, as we'll see. Now I'm going to talk about LTD, which is long-term depression. And if you want to graph the same thing, it's going to look like at 0, at first you're resting, then you're going to depolarize, because that's what stimuli do. They depolarize your cell, but then you're going to hyperpolarize and stay in this negative state. And that's long-term depression. And it usually happens at low frequency for a long period of time. So if you have a stimulus that is low frequency for a long period of time, it's going to lead into LTD. This one is also lasting and non-decremental. Okay, now let's start thinking about the biology that could be responsible for this. In fact, I'm going to change the order of my slides. Let's think about LTP properties that make it a good candidate for storing memory. One that is input specific. What does this mean? It means that if you have a particular synapse and you have a stimulus that's affecting it, and you have another synapse right next to it, and let's say least-here-soma or whatever. If this one is high frequency and leads to an LTP here, that doesn't mean that LTP is going to propagate to this one. This one is still not going to have LTP. It's input specific, meaning that each synapse is independent. If you create LTP in one of them, it's not going to propagate to the other person. Okay, now next one is that it's cooperating. Now this is a little bit weirdly drawn in his slides, which I want to draw your attention to. He draws it like this. You have an axon, you have a bunch of stimulus, and they're low frequency, and you get an LTP because they cooperate with each other and lead to an LTP. The thing to notice in this drawing is that these pathways are actually acting on the same synapse. They're not working on different synapses. This additive property works as long as they're all acting on the same synapse. So I would like to change this drawing to kind of like a big synapse on this huge axis. So there is an additive property. If you have multiple pathways with low frequency, you can think of them as being additive. And you can look more. You can just literally Google LTP, and the Wikipedia page does talk about input specificity, cooperativity. So if those kind of confuse you, do Google it, and the Wikipedia is pretty clear. And lastly, we have associativity. Which means that, let's say you have two different or two different pathways. Normally, if I have a low frequency going on here, this is not going to cause an LTP, right? If I have this by itself, nothing's going to happen, no LTP. But if I pair it with a very high frequency stimulus, then you're going to get an LTP in both. So now I think it's a good place for us to actually go back to the biology of it all and try to explain this using the biology. So let's start talking about AMPA receptors. So on each synapse, you're going to have two different types of receptors. Or like in silent ones, you're not going to have AMPA. AMPA's going to come. That's another story. But most likely on a synapse, you're going to have an AMPA receptor, and you're going to have an NMDA receptor. So how do they differ? This is post-synapse, synapse, and then you're going to have a previous one that's trying to, create an action potential at this other cell. So you have another synapse over here. Once this synapse decides to release glutamate to activate this other cell, you're going to have vesicles that have glutamate in it. So you need glutamate for anything to happen. So the glutamate needs to bind both to AMPA and it needs to bind to NMDA. So if you don't have glutamate, nothing's going to happen. Okay? Once the glutamate binds, then AMPA opens. So AMPA just needs glutamate. Once it binds, sodium is going to come in. And it's going to start depolarizing yourself. Whereas for NMDA, once the glutamate binds, still nothing happens. Because there is a magnesium here that's blocking anything from coming in. Now, for us to remove that magnesium, we need the cell to depolarize. So if you have depolarization going on, or if you have an LTP going on, depolarization is going to expel that away. And once that gets expelled away, NMDA receptors allow, I don't have colored thoughts, okay, NMDA receptors allow calcium to come in. Okay? pathway, which we're going to talk about really shortly. So now let's think about how NMDA receptors actually correspond to each of these properties: input specificity, cooperativity, and associativity. So LTP is kind of obvious because only one of your synapses is going to have the NMDA receptor active. So only one of the synapses is going to have an NMDA. What I mean is that, like, if nothing's happening over here, there is no glutamate binding here. So calcium can't come in anyway. So only the NMDA-R for this particular synapse is going to be activated. So there's no way for it to propagate to the other side. Now, for cooperativity, if you have enough of these coming in, enough of cooperative synapses are stimulating the cell, then you're going to get depolarization. And since you have your glutamate, although it might be very few from each of them, is additive over time, so once you get the depolarization activated as well, then NMDA-R is going to be activated and allow for LTP, through a pathway we're going to talk about shortly. And associativity happens because it's here. So this pathway activates NMDA-R because it's high stimulus. LTP is definitely happening here, right? But if its stimulus is very high, it's also going to depolarize the cell. And since this is weak, so it's not non-existent, this one is just weak. It does give you the glutamate necessary, and the depolarization comes from LTP, and we have back propagating action potential. If you remember from the second lecture, the depolarization that happens in the soma also back propagates to the dendrites. So the back propagation allows for this guy to also express LTP. And that can be explained from the biology of an NMDA-R. So let's actually talk about how NMDA-R leads to LTP versus LTP. So you have your NMDA-R, and it's binded to glutamate. So once it binds to glutamate, and let's say it depolarized the cell, so that the magnesium went off, calcium can come in. Now, either the calcium comes in very brief, large spikes in the case of LTP. So you have a large amount of calcium coming in, and it's for a very brief period of time. Or it's going to come in more prolonged and moderate amounts. So let's say this is a very high amount. Comparatively, this one is going to be less, but it's going to be for a longer period of time. So either it comes in this wave or comes in this wave. In this wave, it activates CAM kinase 2, which is a kinase, which puts a phosphate on something. Or it's going to activate calcineurin. And that's going to affect your synaptic protein. So CAM kinase is going to put a phosphate group in addition to your synaptic protein, whereas calcineurin, which is a phosphatase, is going to take the phosphate out. And this determines whether you get LTP or you get LTP. That's a pathway phosphate to your synaptic protein. I'm just going to erase this because you have a synaptic. Yeah?
Well, what's that word right underneath that?
Calcineurin. It's a phosphatase. Any other ones? Yeah?
What role does the synaptic protein perform in sustaining that kind of like higher potential for ATP?
Oh, it just affects your synaptic protein, whether it's phosphatase or not. Like whether it has a phosphate group or not. And that affects its function.
So do we know the function of the synaptic protein?
So as you get more phosphate on it, more AMPA receptors come and they're more active on top of your synapse. But when you don't have the phosphate group, you have less AMPA, so you get LTD. Good questions. Okay. Now the thing is that so far in his first lecture, he talked about let's have low frequency for a long period of time, or high frequency for a short period of time, where high frequency gave you LTP and low frequency gave you LTD. But then in his second lecture, he talks about, well, how high the frequency really has to be, or how long does it actually have to be. And it turns out it should be like for the LTD, which is low frequency for a long period of time, it has to be for a very long period of time. That's not realistic in your bodies. And for high frequency, it needs to be at a very high frequency for it to actually be effective. So it makes sense for experiments to work that way in inducing LTP, but it doesn't really make sense in your bodies. So he tries to come up with another way to create either LTP or LTD, and that's how he comes to spike timing difference. Spike timing difference. No, sorry. The spike timing dependent plasticity. STTB. No, D. Sorry. Yeah. Yeah, ST. I might be getting this order wrong. So I think it's STPD, but that doesn't make sense. It should be STDP. Anyways, so the way STDP works is because of the back propagating action potential in your cell. So as I said, if these are the dendrites and you have a soma and then you have an axon, if you create an action potential in this, it's supposed to go towards your axon, but some of it actually does back propagate to your dendrites, which allows your NMDA receptor to open. The property of this is that it's fast and it's quite transient. Which gets your magnesium off of the NMDA receptor. The thing is that what STDP describes is that the timing matters. Whether your action potential in your postsynaptic cells happens first, or whether your synaptic input comes in first, determines whether you get LTP or LTD. So in the way that makes most sense to most of you, or it should make most sense to most of you, is that your presynaptic should fire, then your postsynaptic should work, right? So your presynaptic fires, then the postsynaptic action potential happens. If this is the order, which should make sense, you get LTP, as you might expect. But if it's the reverse order, you get LTD. And this goes back to the Hebb's rule and Stent's postulate. So Hebb's rule says that if two cells fire together, they should fire together. Whereas post to pre is more like Stent's postulate, because if your post is working and then your pre fires, then that means they're not really related. They're not correlating in any way. Your pre is not causing your post to fire. So they start to wire out of sync. They are going to lose their okay. Now this plasticity is regulated. Now this plasticity is regulated because you don't want an LTP to cause more LTP, and then you're going to have LTP for the rest of your. So like if there is any sort of feedback loop between your neural activity and your synaptic response, you want this to be a negative feedback. What do I mean? If you remember that example from the cat who sewed, he sewed his eyes. He did his right eye first, and then the left eye first, then the left eye, and then got rid of both of them, and he could still see. That's although the rate of firing in his right eye was quite low. That's because this is regulated. The threshold for causing LTP or LTD is regulated, and it's regulated through this feedback loop, which is more neural activity. Sorry, it's probably wrong. More neural activity is going to lower your synaptic response, and less synaptic response is going to increase neural activity. So it's a negative feedback loop. And he talked about two different theories to explain this. One is the sliding threshold. So if you have this being 0, and this is called the change in synaptic weight. So if this is your normal condition, and this is the LTP range, anything positive is LTP, let's say, and anything negative is LTD. This becomes the threshold, like you have to be higher than this threshold post-synaptic activity to call something LTD versus LTD. LTP versus LTD. So this is the threshold. Now, if I have less activity, so I sewed the cat's eye and the cat's eye is firing a lot less, then you want it to be more sensitive. So you're going to shift your threshold to the left with less neural activity. And the opposite is going to happen if you're firing a lot. Then you want to make it harder to induce LTP. So this is increased activity. And when I say activity, I mean neural activity. Okay, so that's one thing. One thing to know about this is that this is a global model, which means that if you shift the threshold, you're shifting this threshold in all of your synapses. It's not in just one of your synapses. So let me just write global. So you're causing this effect in all of your synapses. Lastly, another theory to do this negative feedback loop is synaptic scaling. So let's say the weights are 1, 1, 2 as far as sizes go, because you have variable sizes. So let's say this is your normal situation. If you become less active, you want to become more sensitive. So less active, meaning less neural activity. You want to become more sensitive. So what do you do? Do you increase the size of the synapses or do you decrease it? I'm sure you know this. I'm going to repeat my question. If you have less neural activity, you want it to lower your threshold, right? So do you increase the size of the synapses to become more sensitive, or do you decrease it? If you're less active, it's a negative feedback loop, right? If you're less active, you want to have higher synaptic responses. So you increase your synaptic weight. Sorry, I know it's late. But one thing to note is that the relative weight doesn't change. Because yes.
When you say neuronal activity, do you mean pre or post-synaptic?
Just general firing rate of your nerves. But mostly it's related to the pre-synaptic. Good question. Any other questions? Yeah.
How do you define neural weight? Is it like the physical synaptic size, or?
Yes.
Okay.
This is synaptic weight, but yes.
Synaptic weight, yeah.
Yeah. It depends on its size, or basically how many AMPA receptors are there to receive. We represent it as size, but it's really related to the AMPA receptors, the number of AMPA receptors. One thing to note is that the relative weight doesn't change. So if it was 112, it's going to stay like 224, because you don't want to lose your previous memory. The relative weight coded something regarding your previous memory. So if you're scaling up everything. Okay. So relative weight the same. And as you can see, this is also global because it affects all the synapses. And then, as you might expect, higher activity is going to decrease your synaptic weight. So it's going to scale it down. I really wish I had picked 3 instead of 2. Okay. So that's the general idea. And this is the whole regulation process. This is a regulation process of plasticity. It's called metaplasticity. And that's it for Kirkwood. Yes? Will stay the same. Stay the same. The relative weight, I mean like 112, the ratios stay the same. And global, I mean it happens to all the synapses. Same thing here. Global means it affects all the synapses, not just one. Okay. On that note, any other questions? Yeah?
What do you mean by pre and post synaptic?
Good question. So remember I drew these things and this one, right? So what is this is called a synapse. This is the presynaptic cell. This is part of the postsynaptic. Any other questions? Okay, have a great weekend.
Talk about Zhang, and yeah, sorry we had to held this today, by the way. Our schedule is not that good this so basically, initial biology portion. Yeah, I don't know if you guys have seen this before, like just a basic neuron. Basically, I think the key things to recognize that, I mean, everyone knows soma, axon, dendrites, right, and those are from here. I think the key thing to recognize in these is that, so we're going to relate the action potential back to this drawing. So basically, when we have an action potential, okay. So that's an issue, but okay, sure. I'll just write it in a note. Okay. Alright, can you guys see this? Alright, it's a little bit messier, but I just did it for improved speed. Yeah. Alright, cool. So, soma dendrites, many dendrites connect to one neuron, and every neuron has one axon, and every axon has one axon hillock that initiates action potential. And then along the axon, most neurons have myelination, which involves essentially these nodes of Ranvier. And so basically the action potential propagates along this axon. And so what that means is that it actually jumps from node to node. So there's not like an action potential happening here. It's here, 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 and so forth. And then one axon leads to many dendrites. All right, so for the action potential, can you guys see this? Everyone? Yeah? I mean, it's a little bit small, but everyone. Basically, we'll just describe it. So basically, there's this resting potential, and that's determined by Nernst's potential. And I don't know, I mean, the lecture doesn't really say it, but I mean, maybe you guys should know. So I think the key assumption for Nernst's potential is that you should know is that it's at equilibrium. So that means there's no ions moving back and forth. So anywhere along the action potential, you can't actually use Nernst's equilibrium because it's technically not at equilibrium. The cell has ions flowing in and out. So the only point you can determine is this resting potential, which is why we know it to be approximately -70, give or take a couple of minutes. All right, so then basically what happens is that we have action potentials coming in from other axons, which travel along these dendrites. And so not every incoming potential will lead to a spike. So that's the all or nothing phenomenon of action potentials. And so essentially initially what you'll get is this little bump. And so this is not an action potential. This is what's called the EPSP, the excitatory postsynaptic potential. And so basically you can think of this as like the summation term, you know, like of all the neurons, say there's a lot of neurons firing, each with some voltage, they'll sum up here, and essentially if it reaches a threshold value of -50, then the preceding action potential will occur. So if it doesn't, it will just essentially come back down, back to resting, okay? All right, so say it does hit the threshold, what actually happens? So what actually happens is, so you guys probably all know that it's, what is it, like sodium in, potassium out. So basically, I think the main details that you guys need to know, because he included one slide on Hodgkin-Huxley, but I think it's probably, he wouldn't ask something that complicated. Basically what happens is that the key thing to know is that these ion channels related to sodium and potassium are voltage gated. And so the conductance okay, so I would like to write everything in math terms. So basically, they're both functions of voltage, different functions. So basically, you can assume that as voltage changes, the conductance changes, and what that means is that essentially the ion channels for each of the respective ions behave a little bit differently at different voltages. And so you start off here and you say you hit the -50 threshold. Essentially what happens is that a collection of sodium ion channels will go from closed to open, and this will happen at a very fast time scale. And so what that will happen, so then more of these ion channels will open. So not all of them, it's not like a snap, everything opens at once. It's some open up, and then immediately it's a cascading effect up until you get up to the peak. And so then, at the same time as the action potential is occurring, you have, okay, so this is sodium. You have potassium also opening, but the problem is that they open up at they activate at a lot slower time scale. And so essentially once they finally open, you reach the peak and you come back down because the sodium gates become deactivated. So they get blocked off by some other molecule. And then essentially the potassium also, because they are slow to open, they're slow to close. And so you get this hyperpolarization effect. And so I think the key thing to know here is that in a hyperpolarization phase, you have two situations. One situation is refractory. And I think everyone should be able to describe what this means exactly. The other one is like, I forgot the exact term, but you need more voltage for action potential. And so why is that the case? So refractoriness happens because of this situation. So if an ion channel gets blocked off, then no matter how high you increase voltage, it doesn't matter because the ion channel, it can't get rid of this blockade. And so at that period of time, you have a sort of a plateau of your maximum firing rate for a neuron. So every neuron's maximum firing rate is determined by essentially this sort of refractoriness phenomenon. Then there's also the issue, the second situation where you're still hyperpolarized, but it's not deactivated anymore. It's just closed. So now you just need a higher APSP to make the action potential fly again. All right. Is there any questions on that? Okay, cool. So I'm just gonna erase this. So I'm just going to talk briefly about the first homework he gave. And I feel like a lot of it was computer exercise, but maybe there's some hidden things that you guys can take away. So basically, you're given 10 images. So X is n by 10, right? Where n is the total number of pixels in one image. And then there's 10 images, right? And so you have this essentially very long matrix, and each column is like an image vectorized. And so I think one of the problems asked what the rank of the corresponding W matrix is. Okay. Let's say W is XX. Is it okay if, do you guys understand this notation? Okay. If you guys don't, just let me know. So W, if it maps from XX, then it's essentially n by n, right? And so the question asks what the rank of the matrix is, and I mean, I don't know how you guys did it, but so one of the ways you can always do is numerically, but then I think what happens if you change the problem and such that the same setup is given, but now that you know that one of the images was just was just a combination of 2 of the images that he gave you. So there's 9 unique images, but the last one is a combination of two of them. Then what would the rank of W be? It would be 9. But so basically the reason that is because here, we'll go over some linear algebra stuff that may be helpful. And so I'm just going to give you some equivalence statements, so that way you can always explain something. I'm not going to give you any if statements. So basically, the rank of a matrix is always equivalent to the number of min-I columns and rows. The rank of the matrix is also equal to and then it's also equivalent to the number of non-zero singular values in the singular value decomposition. So I think a bunch of people asked, how do you compute the rank for that matrix? And I don't know, maybe they had laptop issues or something. Because, I mean, you can do it numerically, obviously, but it's actually rather slow. So I think if you time out the MATLAB code, I think it takes like, 5 seconds or more for the large matrix. If you just type in rank of A. But what's actually easier is you can just compute the first 9, 10, or 11 singular values of the matrix. And once you do 11, you see that it starts to become 0. And so therefore, you can just essentially read off the fact that there are 10 non-zero single values, and therefore the matrix rank is A. So these are just equivalent statements. It's always true, no matter what. So that's kind of useful because he does talk about SVD. And so just to review that a little bit, this is always true. Given any matrix that's n by n, it can be square, it can be rectangular, you can break it down into a diagonal matrix. And so he doesn't really talk about U and V, so let's not talk about that. But basically, sigma 1, sigma 2. Basically, the sigma is always of this form. And this is why you can essentially read off the rank. Because the number of once it starts becoming 0, or if it doesn't become 0, then it has full rank. But the number of non-zero is the rank. Cool. Are there any questions on that? Okay, so yeah, he also talks about linear mapping, I guess. And okay, yeah, we can talk about that. Okay. So, and yeah, I mean, I don't think any of this, nothing would directly be on the test because it's like a biology course essentially, but I feel like you should know these kind of things, like if one of the images was a linear combination, I mean, that's so easy for you to like essentially give off the correct answer, essentially right away. So basically, given a system like this, you have the matrix A. So he talks about a couple of different situations, so let's just break them down. One is, okay. I'll just say you could just do, okay, that's pretty standard situation. Then there's two other ones that he goes into more detail, and probably memorize the formulas, or we can just talk about some of the intuition behind them. So there's two basically the first case is the really simple case where you have a matrix, it's full rank, meaning it has n linear independent columns, meaning it has n non-zero singular values. And so basically, if it's a square matrix, you can just take the inverse of it, right? Because you know that if the rank is full, then you can take the inverse of a matrix because the determinant is non-zero. These are equivalent statements. And so that's really easy because then you can just type in inv a in MATLAB and boom, it's solved. Most situations are not that first case, but most situations fall under 2 or 3. And that's, I think, what you guys did in the homework. And so, I don't know, you have to not derive it. I wouldn't say you have to. But I would know the formulas. So, say, yeah, so I mean, these are the formulas. I think something that might help is if you do need to remember the formula and you can't remember it, just try to imagine if A was square. If A was square, this should essentially work out to become like a very easy case of A negative 1B. Does that make sense? I won't write it. Also, he talks about mean squared error a lot. Maybe, I mean, the derivation is actually I think it's doable on a test, so I'll just memorize it because it's only like a page of lines, one slide, sorry. I mean, you guys don't have to listen to me, I'm just thinking out loud, and I think like this is what I would assume knowing the test. Alright, so yeah, mean squared error, I mean, it's just like a given definition equation. So basically, you have this AX equals B, and so if you're not in the first case, you're never going to be able to fully solve AX equals B. So there will always be some error term. So in these two cases, what actually ends up happening is x minus b is equal to some epsilon. So it's not ever going to be 0 because you can't fully invert the matrix. And so basically what you want to do then to get a good x, to get a good solution, is you minimize this mean squared error term. And so then basically what he does in class is that he does the derivative of this. So to solve for this, 0. And then essentially you just follow 2 macro level steps. 1, you take the partial derivative, and 2, you isolate x. So in, I guess it's like neural network learning, basically there's a couple of, there's this recurring thing called the gain functions. So they all have relatively simple form, but then there's also this thing called the basis functions. So basically, the idea here is that like essentially you get this infinite sum of essentially different small functions, or essentially transformations of the gain functions. So the gain functions, I'll just write them out. Sigmoidal, step function. So I would probably just know what they look like essentially, because they have all slightly different form. Well, maybe there's a good case to talk about. So basically, some nice properties. Some nice properties of the sigmoidal function is that the gradient is always defined because it's smooth, right? So at every point you can take like a tangent line and it can be well defined. The problem with the step function and the ReLU, what's it called, ReLU? Yeah. Rectified linear unit is that at these points, the gradient isn't defined because it's slightly discontinuous, right? And so I think qualitatively, he talks a little bit about multi-layer perceptrons, and so those are what is heavily used today in machine learning. And so those are like layered networks. How do we relate this back? So basically, I think maybe the idea here is that you, by building up a sequence of layers of these essentially perceptrons, so the perceptron equation is so you build up a series. Well, this is like a linear perceptron, but essentially, at each of these layers, you can have these activation functions, or the gain functions. And so these gain function will get determined by essentially what you input into it, right? You feed along some x, and you'll get some y, right? For each of these, essentially. And so now you have essentially a value at each of these layers, and now you continue going. So essentially what you're doing is kind of doing this. So you're kind of getting at an infinite series of summation of a bunch of these gain functions, and that's what the multi-layer perceptrons are trying to get at. It's essentially an infinite basis function, so that way you can approximate whatever function it is, whether it's an image, sound, or whatever. So I think, yeah, being able to explain that qualitatively should help. I'll leave the rest of the things to happen.
I'm in.
So I'm going to go through lectures 3 and 4 today. There's
So in lecture 3, talk a lot about these different ways to encode location orientation. And he talked about 3 types of cells that are used to do this. First type is place cells. All right, these are in the hippocampus. And they sort of come together to create a place field. And what that means is that each cell fires in accordance with a spatial location. So it may be that one cell will only fire when I'm around this spot, a different cell may only fire when I'm around this spot, and it's not going to be the exact location. It'll probably be some Gaussian noise around that. But each cell sort of has its own location that it likes to fire to. Now, a slightly different type of cell that he also talked about were grid cells. And this can get a little bit confusing because they are a little similar. This is in the entorhinal cortex. All right, and these fire in accordance with a periodic location. So the cell may fire at this location, and then it'll fire again at every increment of, say, 10 feet that I walk in the X or Y direction. So what that might look like is if I have, let's say this is a room, and I'm trying to figure out where in the room this cell fires. With the place cell, it may be that, it only fires right there at that one location, and Gaussian noise around that. But with the grid cells, it may be that it sort of fires at periodic locations. So it's not a single location, but it's sort of periodic like that. And because of that, grid cells are called torus attractors. Okay? And the way you can kind of think of that is that a torus kind of wraps around. So if I'm at this location and I walk 10 meters in one direction, I may get back to that location again. So they just say torus attractor because it kind of replicates that periodic behavior. Meanwhile, place cells are usually described as plane attractors because there's really only one location it fires at. Are there any questions about the difference between these two? And the third type that he talked about was head direction cells. While the past couple examples were for location, this type of cell encodes orientation. It's located in the Papez circuit. And it'll fire in accordance to a specific head direction. I'll just write orientation. So each cell has a head direction that it likes and will fire most in accordance to. These are called ring attractors. Much like the torus attractor in a ring, you know, like so, it may be that when you're facing in this direction, that neuron fires a lot right there, and then if you turn your head completely around, you're back at that location or that orientation. So that's why these are called ring attractors. And he talked a little bit about how these types of neurons may actually be connected and may work biologically. What was kind of proposed is that you have a bunch of these head direction cells, like so, and you have some input that you get from your sensory systems indicating, you know, what your head direction is at. And then all of these in a single layer would be interconnected. So this is connected with all the other neurons, and this one's connected with all the other ones. And so you have this sort of fully connected single layer. And the weights of these connections can be described if we're looking at this neuron. Can be described like this. Where the weights to the neighboring neurons are negative, so it's sort of an inhibition. But the strength of that weight sort of will become less negative the further you get from it. And this sort of mutual inhibition can help stabilize a system. It's sort of a way of limiting activity to only a single neuron or close group of neurons. So are there any questions about that? What you'll end up having is that the firing rate of these neurons, if you kind of look at all the neurons and you look at their firing rates, it'll kind of be sort of like a Gaussian where you only really have 1, 2, or 3, or a small group of neurons firing at a time. Maybe like this would be firing a lot, these would be firing a little, and then all of the other ones, the activity would go to 0 because of that inhibition. So that's all there really is to the theory behind these cells. There's a little bit of math behind it, nothing too complicated, some sort of spin-offs of the leaky integrated fire equations. That was pretty much most of it for lecture 3. So we're going to move on to lecture 4. Any last questions for that? Cool. So then he got to talking about in his 4th lecture about how single neurons don't really, can't really carry precise information. Because as we've seen, every neuron has some sort of receptive field, right? It doesn't, if we're looking at place cells, for example, they don't fire at a single location. but rather they fire maybe at a rate of Gaussian with the mean at that location. Or head direction cells. A single head direction cell won't only fire when my head's facing at 90 degrees, but maybe it'll fire a little bit when I'm facing 91 degrees or 89 degrees. So how can we get more precise information to actually reconstruct the actual information that's being encoded in these neurons? The solution is population coding. So the idea is that you'll have a bunch of overlapping receptive fields in your neurons, say in your sensory system, in your hand. Excuse my very poor drawing. If you're looking at the receptive field of several cells in your brain, a bunch of the neurons may have overlapping receptive fields. So if you were to look at the firing rate of all of those neurons, you may be able to say, you know, hey, it looks like this is where maybe I'm being pricked. So that's the broad overview idea of what population coding is. But we'll look at a slightly more formal mathematical view of this. So let's say you have a population of neurons. For most of our examples and most of the examples he had in his lectures, these were neurons that had firing rates associated with reaching directions. So if I were to reach my hand in different directions, you have cells in your brain that will fire according to which direction they're reaching in. So for neuron I, we're going to say that PI is the preferred reaching direction. So for any given neuron, this is the reaching direction in which you get the largest firing rate. We also have D, which will be the actual reaching direction. So this is the actual direction that you're physically reaching in for this example. And we have AI, which is the firing rate of neuron I. So if we wanted to figure out what the firing rate was of neuron I, what we really want to see is that the closer to the preferred reaching direction that our actual reaching direction is, the higher the firing rate would be. So we can mathematically represent this perhaps as a dot product, right? Because if they're orthogonal, the firing rate would be 0. But if the direction of those vectors are the same, then it would be the maximum you can get from that dot product. And as we all know from linear algebra, we could also write this out as PI transpose D. Any questions? Okay, so we're going to define V. This is our population vector, all right? And we're just going to sum all of our firing rates, or we're going to sum all of our preferred reaching directions of our neurons weighted by the firing rates of those neurons. All right, for all of our neurons in this population. And we're simply defining that as V. Now, this value here, V, it is possible that V directly does equal D, our true reaching direction, if and only if the sum over I, PI transpose PI equals the identity matrix. I'm sorry if you guys can't see that on my map. Get over here. So V equals D if and only if summation over I, PI transpose pi equals the identity matrix. And there's a little proof to that mathematically in the lecture slides. You can go and look at that if you like. But if this is not the case, then we can't reconstruct our actual reaching direction directly from the population vector. What we actually have to do is use the least squares method to solve for that. So we're going to take our equation for firing rate, AI equals pi transpose d, and this is over all I, where I equals 1 to n, where we have n neurons in our population. And we're going to construct this into a matrix form, where we have AI n equals p a1 to an, p1 transpose p n equals p. And in this case, p and d are both vectors because they are reaching directions in our example. So this would be a column vector. This is transpose of column vectors stacked, so this is a matrix. We're going to define these simply as A equals P D, where lowercase a, where A is a vector, D is a vector, and P is a matrix. And then to solve for the best fit for D, using least squares, you simply do D equals P transpose P inverse, P transpose A. Sort of just using that pseudo inverse that we defined before. So what this tells you is that if you know the preferred reaching directions of all your neurons, and if you know the firing rate of all those neurons, you can reconstruct what you think the best fit would be for your actual reaching direction with more accuracy than you ever could from extracting information from some of the neurons. Any questions about that? Okay. Some simple linear algebra. So there are other ways that we can think about this. He went through one example with one up. I think he went through maybe a couple other examples, but one that he touched upon was maximum likelihood estimation. So this should be something that everybody learned at prop stats, but maybe it's been a while since this is covered. So the idea is, let's say we have a stimuli, which we'll denote as X. All right, we're going to have a response, which we denote as R. And we're going to have our expected response as Fi of X, where I is, again, neuron I in the population. And as we defined before, that's going to be equal to Pi transpose X. Before we were saying Pi transpose D, in this case, that D vector we're denoting as X. So what we really want to do is we want to find the x, the stimuli, that maximizes the probability that we saw a response given the stimulus. And that's how you would write that out mathematically. And given our prior example, all this would be saying is we want to maximize the firing rates, maximize the probability that we saw these firing rates in our neurons given the direction that we reached our hand in. So we can break this down a little bit. We're going to say that P Ri given x, where Ri in this example may be the firing rate from neuron I, the response to that neuron. We can model that as Gaussian noise model. So it's not going to fire exactly at any one reaching direction, but a Gaussian about that mean. So this would be our Gaussian equation for that. So if that's the response of neuron I, the probability of getting that response, the probability of our overall response of the population would be equal to the product of the response of the probability of the response of the individual neurons. Just working off of the assumption of IID. Now, what we really want to do now is we want to use that equation up there, maximize the probability of R given x. And if you do that, you'll find that it would be sort of equivalent to minimizing the squared loss, the sum of the squared loss. And I think this was a homework question. So everybody should, sort of understand this, but does anybody have any trouble seeing how that follows? Really what's happening here is that if you plug this in here, you get the product of a bunch of exponentials, right? We know that if we multiply exponentials, it's the same thing as the exponential e to the sum of the exponential terms. So you end up getting a summation over the squared error there. And this is negative, so instead of maximizing, you can minimizing, and that's sort of how that follows there. Does that make sense? Cool. That's pretty much all he had for his last couple lectures. So if anybody has any questions.